Good day! I'm Dr. T and welcome to my office. So today I'd like to talk about concentration. When we talk about solutions, we need to communicate not just what they're made out of, but we really do need to communicate what ratio the materials are in. Or I should say how much solute is in that particular solution. So to do this, we use units of concentration, and there are actually quite a few choices that I'll go over and hit the highlights for. The unit that we as chemists like is molarity. Molarity describes concentration with moles of solute divided by liters of solution. This has two distinct advantages. The first is that because moles are involved, we can take the volume of the solution in liters, multiply it by its molarity, and from that we can get moles. This then gives us something we can plug into stoichiometry. Yay, stoichiometry. The second reason is that there are quite a few substances in which the chemical reactivity is actually very similar with given concentrations when expressed in molarity because, it's an atom by atom chemical reactivity. But if it was to be expressed in a unit that wasn't moles, the reactivity wouldn't look to be as similar as it really is. For instance, something like hydrochloric acid and nitric acid, if you're simply looking at the acid component of those, both provide the same number of protons per mole. Therefore, if you know that the molarity of the two are the same, it's going to have the same effect when it comes to the acid part of it. Now, once again, there's more to those molecules than the acid, so there can be other effects. But the general idea here is that knowing the molarity is going to tell you a fairly decent amount of information and allow you to see the similarities between molecules that you would not otherwise see if you didn't look at them on a mole per mole basis or an atom per atom basis. Now, molarity does have one glaring weakness, and that is you need to know moles. In order to know moles, typically you're going to have to find the mass of the solute divided by the formula weight. That gives you moles. Then you could divide it by liters. Or in some other way determine how many moles you have. Now, molarity suffers from a glaring weakness. That is that in order to find moles, you need to actually know what the thing you are looking at is. So if you have a solute that is a white powder and that's really all you know about it, well, that's going to be awkward. You're not going to be able to calculate concentration here in terms of molarity. But sometimes you still need to calculate concentration. Therefore, there are other units of concentration that we use, and we'll still use those even when we do know exactly what we're working with. So there's a trio of units that are all very similar that we typically use, and these are going to be our percent concentrations. And you're like, trio? Yeah, there's a trio. Because we're going to have amount of solute divided by amount of solution. However, there's a couple of ways we could describe amount. So we could do grams of solute divided by grams of solution. This is popular when the solution is actually a solid. Times by 100%, and you get percent. In this case, we would say it's percent m/m or w/w. M for mass, w for weight. The m is a little bit more correct, but yeah, the w's still persist. That said, if everything's liquid, it might be easier to measure them out by volume. So milliliters divided by milliliters. In this case, it would be milliliters divided by milliliters times 100% equals percent v/v in parentheses. Now, the reason that these have to be distinguished is the fact that not everything's density is 1. Most things' densities aren't 1. And therefore, if you have, say, ethanol, you have 1 milliliter of ethanol and 10 milliliters of solution, that would be 10%. But if you were to weigh that exact same solution, it would be 0.7% or thereabouts. And that's simply due to the fact that ethanol's density is noticeably less than that of 1. The last of the three is a little bit squirrely. So in this case, we are going to be using the fact that when the gram was originally defined in the metric system, it was based off of a milliliter of water. And so we are going to make an assumption that is blatantly not valid most of the time, but we're just going to hand wave it away. And that is a gram can cancel with a milliliter, alternatively a kilogram with a liter. Yeah, I know. Not a great assumption. But In this case, we will take grams of solute and divide them by milliliters of solution times by 100% and call this a percent mass per volume, or m/v. Alternatively, you could see w's instead of m's. With these, obviously, three different ways of measuring the same thing. So you could have one substance that would actually have three different percent concentrations, depending on which one you use. Therefore, they do need to contain their labels at the end of them. Now, to make life a little bit more interesting, we actually do have another set of units. These are typically going to be based on the weight per weight category. They're not usually applied to the other two. And these are for solutions that are very dilute. They don't have much solute in them. So we're going to set them up very much like we would do a percent weight per weight, except for the fact we're not going to times it by 100%. So for a normal weight per weight, you'd have grams of solute divided by grams of solution times 100% equals percent weight per weight, or mass per mass, whichever you prefer to call it. However, if the grams of solute's a really small number, instead of timesing it by 100%, we'll times it by a larger number. That way we don't have to deal with any weird decimals. Those would be things like a million. So in this case, if you'd had grams of solute divided by grams of solution times a million, you would get a parts per million. If instead of a million you want to go with a billion, then you would have a parts per billion. These are useful for measuring fairly dilute solutions. Now, as chemists, we prefer molarity, and in that case, if we are dealing with a particularly dilute solution, we can stick a metric prefix in front of the capital M for molarity, and we can do, say, a millimolar or a micromolar or a whatever prefix you would happen to prefer. But either one you use, the key part is simply keeping straight which particular unit of concentration you are dealing with. Now, if you are going to be making a dilution, and that basically means you're going to be adding more solvent, then you can keep track of your concentrations with a fairly straightforward equation, and it doesn't actually matter which of these multitude of concentration units you've chosen to use, or if you've chosen to use ones that aren't on the list I've just given. The equation is going to be concentration 1 times volume 1 equals concentration 2 times volume 2. You might also see this as M1V1 equals M2V2, with the N standing for molarity, which is a type of concentration. They're the same equation. So with this one, the ones would be your starting material, so it would be the concentration of whatever you're starting with, as well as the volume to which you're going to be adding more solvent to. The next one, the 2, is what your final solution is. So C2 would be the final concentration after you've diluted it, and V2 would be the final volume after you've added your solvent. There isn't a number here for how much solvent you actually add. That's simply left as the difference between V1 and V2. Otherwise, yeah, it's pretty straightforward. 4 variables, 3 of them which you know, therefore you can solve for the 4th one. So yeah, that's concentration units. They take a bit of practice getting used to, but the main thing to do is just kind of treat them like compound units and typically solve for whatever you don't know. And with that said, have a wonderful day.